So it is my great pleasure to introduce our own Andrew Fisher, who is a distinguished professor here in the Earth and Planetary Science Department. And so Andrew has a broad expertise on water, both here on Earth and also on other worlds. And so today he's going to talk about his recent results on circulation of water around hydrothermal vents on the floor of oceans in icy moons of the solar system. And this is, of course, extremely relevant to the europa-clipper mission that was launched just a couple of weeks ago. And some people here actually got to see that launch right then. And so we are very, very excited. And that is, of course, very aligned with the goals of the Astrobiology Initiative here. And so without further ado, Andrew, please. Thank you so much for being here.
Thank you. Thank you very much for having me here for this seminar. I'm excited to talk about this recent paper. I also have some additional work that one of my grad students has been advancing, and so you'll get to see some things kind of for the first time. And I'm excited to hear your thoughts and see what you think about this approach. I'll acknowledge our co-authors on the paper that came out recently, and then Ru Akiba, who's the grad student who's advancing this work additionally. So this was the paper that came out a couple months ago. It's open access, and then there's some others at my website. I'll apologize. The website is a bit of a mess. I'm in the process of transferring everything to the new WordPress platform, and that's a little bit of a cluster. But anyway, if you want reprints, let me know if you'd like to follow up, because what I'm going to talk about actually goes back 20 years or so. And so this talk is a mashup, really. I'm going to start with an introduction on hydrothermal circulation on Earth, some of what we know or don't know, then talk about this Ocean Worlds project, and then the final third is on this new work that isn't written up yet. We're in the process of working on the paper right now. What motivated this study was ultimately that I got to join this NASA-funded group. The project title is Exploring Ocean Worlds, and it's 9 co-PIs are planetary scientists who have long-term bona fides in the community, and then 9 of us have oceanographic backgrounds. My PhD was in marine geology and geophysics, and so I went into grad school. I started college in 1980, which was right after the first vent papers appeared. And at the time, even I remember at the time being inspired by those discoveries. And so I've been looking at vent problems, hydrothermal problems, geothermics, making heat flux measurements, and using heat as a tracer to map fluid flow for decades. And the opportunity to mix with this group of planetary scientists and try to apply ideas to ocean worlds was really intriguing. And there's been a lot written about the potential for hydrothermal circulation to occur on a variety of ocean worlds, icy moons, either currently or in the past. But in looking at the relatively small number of papers that were available on that topic, I was left kind of confused about what were the important factors, what's the role of gravity, different gravity on different sized bodies, other issues, some of which are common to studies of hydrothermal systems on Earth, not gravity, but other questions about permeability, depth of circulation, the extent of water-rock reaction, and therefore, when it comes to ocean worlds, the implications for habitability. Now on Earth, we've heard most about these kinds of ocean worlds, these kinds of hydrothermal vents, the black smokers. A lot of folks don't realize the very first vents that were discovered on the Galapagos Mounds area were low temperature vents. The high temperature vents that were published in the 1979 paper in Science were more like these. That came a couple years later. So there's a range of vent conditions. In addition to the very high temperature vents that are mostly found close to mid-ocean ridges or in active off-axis volcanoes, this system was discovered about 20 years ago, 25 years ago. This is the Lost City vent field. These towers that are 100 feet high are made of carbonate. And those fluids that are coming out have a pH of 11 to 13, highly alkaline, very different. They're driven by lithospheric heat loss, but they're augmented by exothermic reactions at a metamorphic core complex where the crust has been unroofed, the peridotite of the mantle is exposed. It's an ultramafic rock. And then you get serpentinization reactions, and that can release hydrogen and methane. And so there's a whole different set of chemical and biological reactions that are occurring around those systems. And they're kind of moderate temperature. And then on the right, though, these are actually the dominant hydrothermal systems on Earth in terms of the volume of fluid. These are systems that are driven entirely by the cooling of the Earth, the secular cooling of the Earth, and therefore the heat just coming up through the lithosphere. They're not directly connected to any magmatic or tectonic activity. They're sort of the background flux. Well, these high temperature systems, the total amount of water moving in and out of the ocean into the seafloor and back again is about 40 cubic kilometers per year, which incidentally is the rate of seafloor spreading and crustal creation, just FYI. In contrast, for these lower temperature systems, the flux is at least 20,000 cubic kilometers per year. And to put that in perspective, that's the discharge of all the rivers and streams in the world to the ocean. It's the same amount of flow. And as a consequence, the water that's moving in and out of the bottom of the ocean, you can imagine that the Earth is breathing in the ocean and breathing it back out again about every 100,000 to 500,000 years. That's the rate of circulation. That number's been well known for a while, but I think equally important is the fact that if you look at the porosity of the upper volcanic crust and calculate the residence time of those fluids, that's around 1,000 to 10,000 years, about the same as the age of deep water in the North Pacific. So the crust going in and out, the water going in and out of the crust is cycling carbon, nutrients. And of course, we should be looking for life in that kind of an environment because you've got rock, you've got heat, you have geochemical potential. Yes?
So just to make sure I understand, it's not my area. You're saying it's breathing and impacting the fluid, or are you talking about gas?
The circulation of the fluid. And there are dissolved gases involved as well. But I'm talking about just a simple back of the envelope residence time calculation. You take the volume of the ocean, you divide by that flow rate, you get the circulation time. Yeah, it's quick compared to the age of the Earth. Now, the Earth is odd in many ways, right, compared to other bodies. But that's what we're dealing with here, at least on this plan. Yeah.
And it's not a steady state, right?
Yeah, that's a steady state calculation. It's certainly changed in the past. During periods when seafloor spreading was faster and sedimentation was thinner, there was more exposure. That cycling time was probably shorter, for example. The heat flux was higher at that point, driving more flow. Yeah, so it's varied through Earth history, for sure. And I will suggest, for the benefit of time for the group, absolutely interrupt with questions to clarify. For implications or big picture, maybe hold them till the end. Okay, no problem. But I'm happy for you to interrupt, especially if I say something confusing or misspeak. Please stop me and we'll visit that. So one thing that folks figured out some years back, probably in the last 20, 25 years, is that it's really important to have variability in the properties of the seafloor to allow this process to occur. Joe Can, a well-known petrologist, structural geologist, and scientist of hydrothermal systems, notes that these systems are discharge dominated. They are controlled by the fact that it's hard for the water to get out. That's what makes them run. And I can follow up with that idea later on. Well, one of the features of Earth's seafloor that allows hydrothermal activity to occur over much of the ocean basins is the presence of permeable pathways like seamounts. And the latest seamount census on Earth suggests that there's something like 10 to the 4th to 10 to the 5th of these features scattered around the ocean. And you can count on one or two hands the number that have been surveyed and investigated in detail. Most of them are too small to show up on those beautiful gravity satellite maps of the Earth. All those maps that show the bathymetry of the ocean with the water removed, the pixel size is 3.5 kilometers. So anything smaller than that doesn't even show up. Most, all over the, and as you'll see, important because they become centers of discharge and recharge for these fluids to make their exchange. The reason they matter is not because they're seamounts, it's because they are permeable pathways. They are sections of the seafloor that are more permeable than the surrounding seafloor. Okay, so this also occurs along faults, along fracture zones, along large igneous provinces. There are other characteristic features on Earth that are permeable pathways as well. And just to show, this was a site that we discovered We originally found it through surveying and heat flow work, and we visited with Alvin and Jason in 2013. And this was some video. We discovered in 3,000 meters water a number of new species of deep water octopus. They brood their eggs in the, if you look carefully, see the shimmering? This water is coming out at 10 degrees C, but it has a refractive index different from bottom water. And so it gives you that shimmering effect. We also have squat lobster, tube worms, crabs. The primary predator here is a vicious shrimp that will attack the eggs of the octopus if the female doesn't surround the egg. She turns herself kind of inside out and upside down and protects the eggs. They brood the eggs for up to 2 years. And we returned last fall and were able to witness and get video of eggs hatching, baby octopus in the deep ocean hatching on these systems. So, you know, as we look at deep sea mining, as we look at other developments on the planet, changes in water chemistry, changes in temperature, these are really important systems that we do not understand, even on Earth. All right, but they provide us with some inspiration for thinking about what could be happening on ocean worlds. So what's, yeah.
So, to my understanding, most cephalopods are very, very short-lived. So
Not these.
Spending 2 years brooding is quite extraordinary.
That's right.
Do you think that the hydrothermal nature of the environment is why they live so long? Is that related?
It could be. On the expeditions last year, we had Janet Boyd out with us from the Field Museum, one of the experts on deep water octopus. And so there's a lot of work going on right now on trying to understand their natural cycles. But like I said, on one short dive, we discovered 3 new species. So this is an unknown environment. I mean, every time corals are brought up, new microbes are discovered, new macroorganisms are discovered, even the octopus, a charismatic animal that we think we know a lot about, and we do in the shallow water, but not in the deep ocean. Right? So they make their homes in these systems, and they're clearly, it's energetically favorable for them to be bathed in 10-degree water when the surrounding bottom water is 2 degrees C. Right? It's clear that's part of what's going on here. But also the bottom dwellers, whether they're sessile or motile, they like a hard substrate. They like something to hang on to, you know, while they're making their living. Okay, so what is driving this system? Well, ultimately, it's the heat coming out from inside the Earth, but it forms what we call a hydrothermal siphon. So again, I'm drawing these as outcrops, but imagine instead of outcrops, they're just cracks. They really could be any kind of a permeability heterogeneity, right? And at one side, you have cold water flowing in, and it's bringing with it all the nutrients, compounds, whatever's in the water, flowing through the volcanic crust in the case of the Earth. There is exchange with the overlying sediment. Now that's important because the sediment is often rich in organic matter. And so as that water flows, you get diffusive exchange, and that's a source of organic compounds to the fluids and the organisms that may live in that underlying crust. And then you get discharge. And we've documented this across distances as great as 50 kilometers, and it could occur at greater distances. There's no reason to believe it's restricted to that. And so what drives this flow is the flow. It is in this sense a siphon, not the classic siphon gas from your car with the tube, but a siphon where the flow itself causes the flow. And that's because the cold water is denser. And therefore, at the base of this cold column, the pressure is relatively high. And the discharge side of the system is warm, and the water is less dense. And at the bottom of that column, the pressure is lower. And so you have higher pressure here, lower pressure there. And if you can get a connection because the medium is permeable enough, then it begins to siphon and it will self-sustain. And it will self-sustain indefinitely. As long as there's enough heat to provide the contrast in conditions and you don't use up all your energy flowing laterally, the system will essentially run forever. So the question that this raised for thinking about ocean worlds was, are there conditions like these that could operate on ocean worlds where gravity's lower? And when we started to look at the papers, we were confused because every model was specific to a particular ocean world, which makes sense. That's what's motivating the work. But it was confusing because we couldn't tell what factors matter. Was it the depth? Was it the gravity? Was it the amount of heat flow? Was it the presence of a conductive boundary layer at the bottom? We couldn't figure out what was driving or allowing these systems to operate. So what we thought we should do is take a system on Earth that we understand, just change gravity. Right? So that was the original idea. And originally, It was a thought experiment and a proof of concept that kind of blossomed into a study, but the goal was just to get some intuition about how these systems could operate if gravity were different. That was the modest goal. So we began with variations in gravity and then added a few other variations in things like permeability and the heating from below. So here's the field site that became the basis for the simulations. This is in the Northeast Pacific Ocean. Here's the Juan de Fuca Ridge, the Cascadia subduction zone. Vancouver Island is up here, and that yellow box is this area over here. And if you look really carefully, you see that tiny dot? This shows up in satellite gravity data, which is what you see here. And that's this outcrop, Grizzly Bear outcrop. It's about 5 kilometers across. 50 kilometers away to the north is a tiny little outcrop, which has been named Baby Bear. And what earlier research found is that cold water comes in here, flows 50 kilometers, and a fraction of that water pops out here. There are also vents on these other larger outcrops located about 16 and 20 kilometers to the north. And very quickly, here's some of the evidence. There's other evidence as well. These are seismic reflection profiles across the two features. They are to scale. Baby Bear is actually a significant edifice, but only the tip of it sticks up above the surrounding sediment. And heat flow measurements made adjacent to Baby Bear's skyrocket. These are in milliwatts per square meter, so that's 1 watt, but we've measured with a short probe and a submersible up to 60 watts per square meter of conductive heat flux coming out through the top of that feature. The only way you do that is to be bringing warm water up from below. And in contrast, at Grizzly Bear, the background heat flux is about what you expect for seafloor of this age, around 200 milliwatts per square meter. But right adjacent to the outcrop, it drops by half. It doesn't look like much, but that's a huge drop. There's basically a geothermal moat around that side of the system, and that's the evidence of the cold water going in, right? And then we were able to show through some analytical calculations that these potentially could connect. But then about 10 years ago, I got to work with Dustin Winslow here at Santa Cruz, and he and I and others put together the first 3-dimensional ridge flank hydrothermal models for the Earth. And this was to test this idea that you could create a hydrothermal siphon with this process. So it's a very idealized domain. It's set up for a finite volume coupled fluid heat flow model. It's a transient model, so it allows oscillatory behavior, unstable flow, and so forth. The two outcrops are idealized, but these ziggurats have exactly the right surface area at the top, and they have the right angles for the sides. So they capture the fundamental nature of those features. And we put this in a big domain. We've got sediment mostly covering about 450 meters of sediment at the top, but not where the outcrops poke out. We put in hydrothermal aquifer layers and varied the thickness, played around with permeability, other parameters to see, could we drive flow? We added heat at the base. In this case, it's around 200 milliwatts per square meter based on the age of the seafloor. That's based on standard cooling curves and measurements made regionally. When you're away from the outcrops, you measure lithospheric heat flux. And indeed, these models led to the spontaneous formation of a hydrothermal siphon. This is a cutaway. The large outcrop is here. The small outcrop is 50 kilometers away. And this just shows flow vectors in the edges of the cutaway section. We get recharge at the big outcrop. You can see the cooling, that blue area down here. Most of the water turns around and comes right back out the top. And in the surveys we ran last fall, we found warmish water coming out of the top of one of these big outcrops where there was a skate nursery. A bunch of deep water skates were brooding their eggs in that one. Okay. Meanwhile, a fraction of the water heads to the north. It's actually mixing as it goes. And then at the small end, you get the discharge. And we were able, by tuning the model, to match the observations. And the key observations were the heat output and the rate of fluid flow, which has been determined from the plume of warm water that comes out over the smaller outcrop. And in order to match that set of constraints, we needed an aquifer that was no more than 600 meters thick in the upper part of the silicate crust, and a permeability that's about 10 to the minus 13 to 10 to the minus 12 meters squared. Now, unless you mess around with permeability a lot, that number means nothing. So let me just take a minute to talk about permeability. It's a measure of the ease of flow. Although it's often presented as if it's an intrinsic property that can be derived from other properties. It cannot. It's an emergent property. It only has meaning in the context of an experiment or the natural world in which flow occurs. You provide a driving force, you measure the flow, you back calculate the permeability. This is what it means, and you can't really boil it down. What it means is, in practical terms, we have a very hard time figuring out what permeability is unless we can measure it directly. This is a challenge for ocean world calculations. Even for Earth's ocean, this is a compilation of data. This is all the permeability measurements in the seafloor over 40 years, 40-year period. And this is a log scale. This shows 7 orders of magnitude, but in natural materials, permeability varies by 15 orders of magnitude. So we and the astronomers have something in common, that we work with a range of orders of magnitude, right? This is everything from the liners to landfills at the low end to rubble and the upper ocean crust at the other end. So that's a log scale. This is depth into the basement rocks, everything below the sediment. And you can see that in general, the upper part, the upper 300 meters certainly is the most permeable, highly variable, often within thin zones, probably having something to do with layering, faulting, and other small scale heterogeneities. But it's the relatively high values. This is the range of values that we found for that study. And it's these relatively high values. And in that case, if we went higher, then too much water flowed and it chilled the basement rocks and it lowered the heat flux, which is not what we measure. So there, the permeability provides a powerful constraint on what we think occurs. Also, as part of the study, we ran a railing number analysis just to investigate what we might expect. So in this case, I took the properties of the area around the 2 outcrops and then applied different values of gravity. Earth, the gravity for Europa, it's about 1/7. And then the gravity of Enceladus, about 1/100th of Earth gravity. And here's the calculated railing number as a function of the permeability of that aquifer system. And 2 critical railing numbers are shown. The upper one is for a box that's sealed at the top and the bottom. So that would be internal convection. And the lower one is for a box heated from below, but open at the top. So it allows water to come in and come out. So nominally, you have to exceed these values in order to initiate convection. Right? That's the concept. In fact, what we see for the case of Earth, for a 600 meter or a 300 meter aquifer, we're way up here. And we have hydrothermal siphons. And this suggests to me that maybe it's harder to make a siphon than it is just to initiate convection. Right? The fact that where we're at in the system is it's well above the critical railing number for internal convection. And we have siphons here. And if we simply shift this box based on the expected gravitational acceleration on the seafloor of Europa and Enceladus, then you'd think we would need about an order of magnitude higher permeability in each case to generate a similar set of conditions, right? So it's not a prediction, but it's saying, well, this is kind of what it seems like we would have to get equivalent conditions to what we have on Earth. And this made us wonder, can we even get a hydrothermal siphon if the permeability is not that high? What if it's lower, but gravity's low? So what we did is dust off these old models and make some minor modifications to the grid, and then also get a copy of the source code for FEHM, the hydrocode we've been using, and find every instance of gravity, turn it into a variable, and then start changing it. So we basically recompiled the code with gravity appropriate for Europa, gravity appropriate for Enceladus, and then started to play to see what happened with the different conditions. So we varied the permeability of the aquifer system, and here I've marked what the Earth values are, roughly. The permeability of the individual outcrops, we ended up leaving that one alone, just set it to a high number. I can talk about why. We tested different thicknesses, that's the depth of circulation and the thickness of that aquifer unit. And then heat flow. We started with the same heat flow as on Earth, about 200 milliwatts. Then we cut it in half, and then we cut that in half again. So the range is relatively high compared to Europa, for example. It's sort of in the ballpark, maybe for Enceladus. We'll come back to that towards the end. So really important, these are not ocean world models, right? These are models of the Earth system with ocean world gravity. I want to be clear. Okay, because we didn't try to replicate conditions on ocean worlds in terms of the depth of the ocean, the pressure boundary condition, and so forth, right? The whole premise of this was just to figure out how much does gravity matter, everything else being equal.
The same concentration in salt, like.
Sure, sorry?
The same concentration in salt and the same composition of water.
Yes, yeah, so everything else was the same. Again, I don't think the bottom of Europa is made of basaltic ocean crust. That's not the point. But we just wanted to change one thing at a time to try to understand how the gravity impacts the systems. And then we can start to make more changes and put in more realistic other conditions, right? That was the concept. Yeah.
And so is the system always symmetric or is mounts are one of them bigger than the other?
Yeah. One is bigger than the other, and that's because that's the way it is in the field.
Okay, one is taller than the other?
It's taller and it's wider.
All right.
Yeah, and I can talk about the significance of that for making a siphon, if you want to talk about that at the end. I just don't want to stop now because I want to get to the ocean world.
That's driving the pressure difference.
Pardon?
It sounds that drives.
Yeah, but that's a hydrostatic pressure. So if you just spin up a model with different heights, but without the heat input at the base, without the full coupling, you will not drive flow.
Right.
It's different pressure, but it's a hydrostatic. Yeah. Okay, so I'm going to show you a couple of figures that look like this. So you're now looking down from above, and after the model was run, I just stripped off the sediment so you could see the aquifer below. And then I plotted up vectors, and they're proportionate to their flow rate, but they're on a natural log scale, just so you can see them more clearly. Also, only 20% are plotted, because if you plot them all, it just looks like a pile of straw. You can't really see anything in that. And then I took a cross section through the middle that runs through both outcrops and just elevated it so you could see it. And that's what you're seeing here, and that's scaled by temperature. So once again, at the recharge side, you've got this blue moat. That's the signal of recharge. That's the cold water going in. Most of that water turns around and comes right back out through the top, but a fraction of it spins along and it heads to the other outcrop, and it's mixed convection along the way and then pops out here. And you can see these little plumes. Those are not stationary. They roll. They form, they break up, they form again. And you can see the small scale convection throughout the entire system. It's kind of knocked down right here as water flows in and then away. It actually forms a dipole with water with net transport on either side of the outcrop. I'm going to give up on that. With water on either side of the outcrop. And indeed, there's even backflow, which goes here, goes all the way around, and it comes back in the other side. So it looks very much like a magnetic dipole, right? It's a hydrothermal dipole. The temperature in this case this isn't exactly like the Earth system. It's a ballpark number here. So it's a tad warmer at the upper end of what we think the Earth does. But we've essentially just replicated the earlier models with the new code. That's the first step. And then here's a comparison. This is the same simulation you just saw. And now this one has the gravity of Europa, and it's a thicker aquifer. This is the gravity of Europa, and it's a thin aquifer like this one, but it's deeper. And then this has the gravity of Enceladus. These are just some examples. We ran 60 sets of simulations with a range of different conditions. They all show the mixed convection, although when you get to the very, very low gravity, it's weaker. So it's a lot harder to see here thermally, but you can see the effect of it out here with the vectors. You'll also note this area of lateral flow is much wider here than it was under the Earth conditions. It's also wider here under the lower gravity conditions of Europa. So what's happening is the secondary convection is being suppressed with lower gravity. And that kind of makes sense. There's less buoyancy, right? That secondary convection is a parasitic loss for the siphon. If there's enough lateral convection at a small scale, separate from the flow through the siphon and out the other side, then the siphon will collapse because you've used up all the driving force. So this is one of the key parameters for maintaining the system is you have to have enough driving force, and that's a function of buoyancy, but you have to have not too much loss from the secondary circulation. Okay, so let's look at this. Instead of these complicated vector plots, let's just look at some metrics. Here's the temperature of the siphon at discharge. And the original slide I showed you was here, right? The one for Earth is right here. And now here are different gravity values. Gravity for Earth, gravity for Europa, gravity for Enceladus. And what you can see is there's a modest temperature dependence. When you go to lower gravity, the lateral flow slows down and the water has more time to warm up. But it's a small effect. The difference in gravity is a factor of 100. The difference in temperature is about a factor of 20%. Right? So it's a modest effect, but monotonic, you see in this case. When the permeability is low enough, this is actually less than what we think it is for the Earth system. If you go to lower gravity, then the siphon fails. Right? We start out with a higher permeability and we dial it down and the siphon just collapses. Okay? It won't run. Because the focus here is not on initiation, it's on sustainability. Okay, here's the same plot. And now I've added the siphon flow rate in kilograms per second. For the Earth system, it's a little fast, but generally in the right ballpark. Very high permeability, though. You get up to 600 kilograms a second. And this drops off quite rapidly as you go up to lower gravity. So again, less buoyancy. You have less flow, but it doesn't kill the siphon. So that's quite different than what we might have inferred from the Rayleigh number. In fact, even when the Rayleigh numbers are relatively low, we can still connect. We can still create a siphon, even with permeabilities that when you look at the Rayleigh number analysis, you might think, I'm not sure we're going to be able to sustain that. And then finally, the same two plots you just saw. But now here is the advective heat output of the siphon. That is the temperature difference between the discharge and the bottom water, the flow rate and the heat capacity of the water. And we're getting at the low end a few megawatts, but at the high end up to 150 megawatts. Again, it dies off as the gravity goes down. So bottom line here is that lower gravity, you get a warmer flow, but you get less heat, you get less water. Here are the same simulations, but now we've got a thicker aquifer, twice as thick, goes twice as deep, or the same thickness, but it's deeper. So a deep, thin aquifer. Again, I say deep, but it's still the upper part of the crust, right? The maximum penetration is around 1,200 meters into the silicate rocks. And now we see a monotonic increase in temperature with greater depth, but we get a much larger increase when we have a thinner aquifer. And that's because you're not mixing the shallow water with the deep water, which tends to bring the temperatures down a little bit. And of interest for habitability, just FYI, we're in this general range, 70 up to say 150, anywhere within here. So some models have been run that generated a range in this sort of habitable realm with very deep circulation into Enceladus, for example, the Chauvet models. I'll show a picture of that later. But you don't need to circulate all the way to the core of Enceladus to get 100 degrees or 120 degrees. It can be shallow if there's enough heat, right? But it doesn't have to go deep. Here are now flow rates for, again, the deep thick and the deep thin aquifer, and they're higher. We can get close to 1,000 kilograms a second, and here over 2,000 kilograms a second. The slide I showed earlier with the flow with the octopus, we estimate the output there is around this range, on the order of a couple thousand kilograms per second. So again, just putting that in perspective. Much lower flow, though, with lower gravity, right? Again, less buoyancy. The siphon doesn't break, but it slows way down. And then this shows the total heat output of these simulations, and these were the highest we included in the study, up to 700 megawatts coming out of a single outcrop. That's equivalent to one good-sized high-temperature vent field. Put that in perspective. Here are some lower heat flux cases. In general, the temperatures go down as we cut the heat flow by half, and then we cut it by half again. The flow rates go down and the heat output goes down. Not a surprise, but they don't go down proportionately. So you can cut the heat flow by half or cut it by 3/4, and you still get significant heat being carried. You still get significant elevations in temperature, but certainly not at the same rates, not at the same temperatures that we saw under the Earth conditions, right? Including the Earth's heat flux. Okay, so how do we summarize all of this? I mentioned before the driving force, what I call here the siphon force, and that's just the difference in the density at the bottom of the two columns. But all the other forces in this diagram are losses. And this is energy lost flowing downward and convecting, energy loss flowing laterally and convecting, and then energy loss flowing vertically and potentially convecting. All of that is energy being used up without driving the siphon, right? So when will this system operate? It'll operate as long as the magnitude of this term is greater than the magnitude of the sum of the other terms. And what's left is what we call the siphon pressure, right? That's enough. And as long as that's above zero, game on, the system will continue to run. Now, that's not 100% true because it's oscillating. And so sometimes you can get collapse because of that instability, right? So when you're right at the edge, it won't necessarily continue. But you need to have enough driving pressure to overcome the parasitic losses. A couple of metrics that were interesting. The chemists were particularly interested in water rock mass ratios. And so this is a measure that's often used when people look at alteration in rock or they look at hydrothermal fluid. They calculate chemically how much water rock exchange there's been for particular elements or particular isotopes. This is a calculated physical water rock ratio per billion years of flow. Typically, when you look at a rock, it's integrated over the life of that rock. So probably these are best considered in relative terms rather than in absolute terms. And I'm only showing here 4 sets of models, the shallow aquifer and the deep thin aquifer, and just 2 ranges of permeability, just so the plot isn't all cluttered up. And in general, the water rock mass ratios go down by orders of magnitude as we go to lower gravity. That seems to scale, as you might expect. And then this is a calculation of the heat output of the siphon relative to the heat in of the entire domain, just to see how efficiently we're extracting heat from the body. It can get up to 10 to 30% for Earth, but as we head down to the lower gravity, like you'd find it in Enceladus, you're down at 1% or lower. So much lower efficiency. That's actually kind of interesting because one of the questions that's come up is, how is it possible for a small body to retain hydrothermal activity over a long lifespan? Well, maybe it's a bit easier if you operate inefficiently, right? You can operate a siphon, but not extract that much heat. 2 other metrics we looked at: how many siphons could you sustain on one of these bodies just purely based on the estimated heat output? We know the heat output of Earth pretty well. It's like 40 to 44 terawatts. We don't know the heat output exactly of the ocean worlds. And there's a big question about how much of the heat is coming out from the silicate interior and how much heat might be generated in the icy shell or even in the ocean. And so we don't know how to partition them, but we've made some estimates. And again, conditions kind of scale with the gravity. So on Earth, we can, sure enough, sustain like 10 to the 4th to 10 to the 5th siphons, just about the same as the seamount census. That's kind of a coincidence. We don't think this system is like the average for the Earth. Just kind of came out that way. But many fewer could be supported on Enceladus and fewer could be supported on Europa. If you calculate then all the flows and what the residence time of the water in the ocean would be, this is a very speculative thought because these are not ocean world models, right? What you find is the circulation time is quite fast on Earth, approaching 1 million years. We think it's shorter than this in reality, but again, that's just for these models. But they're similar for Europa and Enceladus, despite the fact that Europa has a much bigger ocean. It's much bigger than Earth's ocean, right? But the difference is there's kind of a trade-off here. You've got a bigger ocean on Europa, but you've also got a higher buoyancy, higher gravity, and whereas on Enceladus, you've got a smaller ocean, but gravity's lower. Anyway, they about cancel out, give or take. In any case, though, the circulation time is quite long. This would be 1 billion years right here. So these are sort of hundreds of millions of years in that realm, right? Long circulation times. And that might be important if you're wondering about whether the ocean is at chemical equilibrium with the interior, right? If it hasn't been in and out a lot, then maybe not. Maybe there's still some geochemical potential. These are figures from the Chauvelet paper of simulations of the core of Enceladus. And I just wanted to note that in the case of our models, they could be parasitically placed on a heat flow high that's generated by a whole core model, right? Who's to say? We don't require that the heat input at the base of our domain be the average of the body. if there's another circulation system that goes deeper, that could partition the heat. And then you could easily have a system like this that is itself parasitic sitting on top of it, right? All right, so let's answer the questions we started with. Can a siphon be sustained at low gravity? Yep, we see that across a range of gravity. What are the temperatures and flow rates? Well, we're getting on the order of up to 150 C, up to about 2,000 kilograms a second, and up to 700 megawatts. And what are the implications for ocean worlds? Well, in general, at lower gravity, we're going to get higher temperature, we're going to get lower flow rates, but we don't kill the siphons. They seem to be able to operate despite the fact that there's a lot less buoyancy. And again, I think this is mainly because we don't have secondary losses. If we had equivalent secondary losses to what we see on Earth, then those siphons would collapse, just like they do on Earth if you dial down the permeability lower. All right, so the last bit here, I'm going to show you something new, and I'll go quick because I know we're going to be at time here. Those simulations took a long time to run. Those coupled models are expensive computationally. So we barely scratched the set of options that we could look at. And what about if gravity was higher, like a super Earth? Yeah, good question. We'd need to recompile the code for a bigger body, right? So, but how can we do this more quickly? So Rui Akiba, a grad student working with me and with Francis on other projects, put together some analytical calculations that we laid out and then put it into a Monte Carlo framework. So let me show you this. This is work that we've pretty much finished, but we're in the process of writing up, and hopefully we'll get submitted in the next few months. So we model the same system, right? And there's a lot of parameters, different depths, heights, different cross-sectional areas. There's a conductive boundary layer. We have different permeabilities and so forth. The conditions here are going to depend on the conditions at the outflow and the inflow. If the flow is fast enough, it's isothermal. If it's too slow, it's conductive. And if it's in between, then you end up with a curve profile. And so how fast the water flows is then going to determine the temperature distribution at the inflow and outflow, which will then determine what we're going to see, right? These are then linked with a, oh yeah, there it is. So the driving pressure is the difference between the two columns, and that's calculated based on the flow rate. And then in between, what we do is set up a calculation based on discharge potential theory, which has been used for geothermal heating and cooling systems. In essence, if you have two wells, one that pumps cold water in and one that pumps hot water out, or for cooling, you send the hot water down and you get the cold water out. You can calculate then the flow pattern in the surrounding area, and it looks like a dipole. And about 50% of the flow will occur within a disk defined by those gold bands. And so on that basis, we can calculate the flow rate and then calculate the efficiency of heat extraction. And so sort of estimate in a very quick way how this would work. Okay, so let's see what that, oh, there we go. Let's see how this works. So each dot is a calculation. So there's 10 to the 5th calculations or so done, and this runs in about an hour. So we can explore a lot more parameter space than we could. It took 2 years to run the models I was running, mostly because I didn't spend as much time, continuously shepherding, but they take a long time to run. So this is a comparison for flow rate versus permeability, and every dot is a successful hydrothermal siphon. In the white is where the siphons failed, they collapsed in the analytical. And then the colored triangles are the results of our numerical models. So first, the analytical calculations can match the numerical models that are, in other words, our numerical results are in the cloud of possible analytical results. And if we look more carefully at the temperatures as a function of flow rate and the heat output, we match reasonably well. But you'll notice there's a lot more area in here that we did not see in our numerical models. But the numerical models, the way they run is if there is excess energy, they'll flow faster, and that will reduce the temperature. So they self-regulate, right? They're fully coupled transient models. The analytical calculations don't do that. With the analytical calculations, we put in a flow rate, and then everything is a consequence of that, right? So one way to think about it is this is the band that seems to match our numerical calculations. And that's where we let 10 to 50% of the energy be lost to the secondary convection. So we're pretty comfortable saying, yeah, let's assume that when we run an analytical calculation, we discard any simulations where if there's more than 50% of the available driving force is going to get used up. It's not being used to drive the siphon, then we're going to shut that one down. We're not going to accept it within this framework. Okay? And it's not perfect. There are some that failed numerically that do succeed analytically, and they're along this trend. And this is in part just because of the lack of coupling with the analytical model. It's done in a very much of a linear fashion. In essence, part of what happens is as the flow rate goes up, then you chill the recharge side, and that can drive up your pressure. But if you get enough flow through the system, then you start to chill the discharge side, and then you lose that excess pressure. So there's a sweet spot, and that's what the numerical model finds, and presumably it's what the real world finds too. Nature tries to find sort of optimize the amount of energy it can get out for the least expenditure. And analytically, we don't do that, but numerically we do. So here's just some examples. This is a set of calculations for much lower heat flux, something that might be appropriate, say, for the core of Europa, right? If it's purely radiogenic or maybe a small amount of tidal heating. And here are gravity values for a super Earth, Earth, Europa, and Enceladus. In this case, you let the calculations go to 10 kilometers depth, so it's about 8 times as deep as the numerical simulations. I'll note that there are many dots you don't see. So the red dots, they actually go all the way up here, and here's the edge of the red dots. Okay, and the blue dots go all the way up here, and there's the edge of the blue. So we see this big range of temperatures, but certainly with higher gravity, we can get larger flow rates, but the temperatures do tend to be lower. Again, when you flow faster, you can cool the system down while you extract heat very efficiently. If we look at the temperature as a function of depth of circulation, again, for the super Earth with even more buoyancy, things tend to level out at relatively low temperatures because the system goes really quickly. Higher buoyancy means a faster siphon, and that's going to chill the opposite, right? Because you're recharging the cold water. At the other extreme, for the gravity for Enceladus, you almost follow the geotherm at the limit, right? We get simulations right at the edge here. They're running, but relatively slow flow rates, and they're essentially just giving you the geothermal gradient, right? Because almost no energy is being carried by that water, just a tiny bit, because they're flowing so slowly. And here's just one more case of interest, potentially. In this case, he locked in conditions that might be appropriate for Europa. We put seafloor pressure of 130 MPa. That's involved in the equation of state for calculating the fluid properties. Circulation depths up to 10 kilometers. It's been suggested that maybe because of cracking, you could get down to 25 kilometers on Europa. Low heat flux, again, much lower in this case than what we used for Earth. Remember, the Earth models got up to almost 200. The heat flux here is 6.5 milliwatts per meter squared, so much, much lower. And then if you add in 2 more constraints, we're interested in temperatures between 80 and 120 and a water-rock ratio from 50 to 150, leaving some of that rock unreacted, for example, then you get these bands. So what's really nice about this approach is you can target areas of interest based on habitability, based on geochemical potential, whatever you're interested in, and now zero in on the family of simulations that ought to work. And now we can investigate those numerically. That's really the idea. Use this to explore the space. We started out trying to plot up distributions for all, we have up to 12 free parameters in the Monte Carlo analysis, but because we have no constraint on most of the properties, what you end up is a uniform distribution for everything, right? So it's not going to help us to tell what's the most probable, but it is really useful for telling us what's possible, right? And that can lead to more exploration. So that's essentially what I say here. Rue and another grad student, Kristen Dickerson, are in the process of putting together some domains that may be appropriate for Europa and Enceladus. There are special cases now to look at there. In the case of Europa, we've got low heat flux, high pressure at the seafloor. In the case of Enceladus, the seafloor pressure is only 7 MPa, so we could get flashing to steam, for example, or the presence of a non-condensable phase like bubbles of hydrogen or something like that. So there's a lot more to explore here, right? But now we have a better sense of how to do that. And as part of the Ocean Worlds project, and hopefully continuing work with that group and with others, these results can be impacted by what the chemists and the microbiologists and others are interested in terms of habitability conditions. And our results can also feed into their calculations as well. So with that, I'll just acknowledge the folks who have funded the work, and I thank you for being here on a Friday afternoon, and I'm happy to answer questions.
Questions? Yes, Ben?
Yeah, in addition to transfer of heat, have you thought about transfer of salinity? I mean, typically people, what they do is to think about the bottom of the ocean and how much that you have and interactions with water, and you count the production of salts and then make an estimate, right?
Right.
I wonder, I assume, right, that having multiple of these systems, right, distributed throughout the seafloor of, say, Europa or whatever else, will increase the area contact of water and silicates, and will have slightly maybe more efficient production of salts, which is quite interesting. So I was wondering whether you have thought about that at all, and whether there's some energy that can support.
Yeah, so this is the ultimate goal. You know, as part of the Exploring Ocean Worlds project, one of the intents is to provide information that could be detectable signatures of a whole variety of processes. So what you know, beyond the Clipper, that system is launched, and we'll learn a lot based on those measurements. But for the next missions, what should we look for? What should be the features, right? That's the question. And so that could be everything from the salt content of the ocean, the dominant salt phases, you know, which minerals are dissolved. Is it a carbonate ocean on Enceladus, as some have suggested?
Well, your time for Clipper, it is a level 1 injection to detect the salinity of the ocean from the magnetometers.
Yes, right. So yeah, so there's going to be information, but I'm just saying, you know, in a way, part of the goal for the overall program was to provide additional predictions or additional constraints that could be applied, right? And potentially help to guide the design of what instruments would go on future missions as well. So sure, we're interested in that. The challenge with full reactive transport modeling is that these already have, you know, 12 to or so free parameters, which we've, you know, parameterized or put into ranges. As soon as you start with reactive transport, there are even more, right? In terms of the topology of the network and the you know, the shape of the fractures, the specific surface area. So absolutely, we're interested. This is really a starting point because we just wanted to be able to figure out what's plausible. But yeah, absolutely, we'd love to see that feed in. What I'll say is, though, if that's going to influence the chemistry of the ocean over long time periods, I'd say the best approach is to take this kind of output and feed it into a separate offline model for reaction. Yeah, right, for batch reaction, because it'll require fewer assumptions in the modeling framework than trying to make these models or models like these fully reactive. Yeah, so absolutely, it's without doubt, that's where this should hopefully go. Yes, please.
I'm intrigued why you chose Kepler 22b as your poster child for super Earths. I think we don't have a mass for that object. So
Okay.
I don't know its Earth gravity.
Yeah.
However, more recently, we do have a slew of super Earth category planets for which we do have radii and masses.
Oh, good.
Some of them even have spectroscopic information from the spheres. And with Artem support on the interior models, some of them are really good candidates for water worlds.
Yeah.
So it's been really interesting.
Yeah, it was a random selection. I trolled a few exoplanet sites, and I looked for a nice NASA image that seemed like it would fit my color scheme. Yeah, I didn't pick it for a particular reason, but we should choose one that's more relevant.
That would be
Absolutely, yeah. So I welcome suggestions, and I look forward to learning more about exoplanets that are good candidates for having water. Yeah, I agree. Oh, David, please, yeah.
Yeah. You drew the input and output as kind of a current. And I wonder if you put some fluorescein into the input.
Mhm.
What fraction of that
Yeah,
would come out here? Because there's gotta be turbulence and mixing and diffusion.
absolutely. So the question is, if you track parcels or particles, what would happen? We haven't done it in this study. In an earlier study of another Earth system, we did do particle tracking. And indeed, many of the particles just end up bouncing around inside the aquifer, essentially until we stop running the model, and a small fraction pop out the other end. And what we didn't do there was try to trace the distribution. Folks who look at groundwater residence time, though, have noted, there's no such thing as an age for groundwater. What there is a distribution, and it's often a distribution with a really long tail. So, and to put that in perspective, when folks have done carbon-14 dating of groundwater, for example, what they find is that because of the irregularity and intricacy of the pathways, the amount of carbon-14 that you lose by diffusion is orders of magnitude greater than the amount of carbon-14 you lose by radiometric decay. So it means that water that's interpreted to be 10,000 years old might actually be 10 years.
Quick follow.
So it's it's a great question. And again, the thing that makes my head hurt when I think about it is that we just, even on Earth, we do not understand what these pathways look like. Even in the most homogeneous aquifer systems like dune sand, there are variations in properties of 1 to 2 orders of magnitude commonly. So when we get into things that are, say, fractured media, like perhaps the core of Europa, or maybe a granular material that's not even coherent in the core of Enceladus, what does that look like in terms of the network of pore spaces? I have absolutely no idea. I just don't. And it could be fun to play with it, but it really, I don't think in our lifetimes we're ever going to know. And I think maybe the approach to take is to say, well, let's try some plausible geometries, some plausible porosity networks, and just see how much they matter, right? Because even with data, again, like on Earth, we don't know. No one knows what the plumbing of an Earth hydrothermal system is. They just, in papers, they just look like this. They look like circles, because we don't know.
Quick question.
Oh, yeah.
Before Dave asks
Yeah.
the question, I want to make sure that people feel free to stay and ask more questions, but also to take advantage of this amazing spread.
Yes.
That Artem and Noémie and Caitlin have put together. So please mingle and socialize and ask lots of questions.
Thanks. Yeah. Yes.
Yeah, I do have an interesting last question.
Yes.
Does your analysis have anything as explanatory power for the plumes? Are they
Yeah, so short answer is not directly, but in our paper, in the Exploring Ocean Worlds group, we're working with some physical oceanographers, and we looked at some metrics for buoyancy flux, for example, just like have been applied to plumes on hydrothermal systems on Earth. So on Earth, you can have a high temperature hydrothermal system, and if you drag a thermistor chain through the water column, hunting for it, if you're 50 meters off bottom, your typical thermal anomaly is maybe 10 milli-K. It's tiny. So even a high temperature vent field has a buoyancy flux that's insufficient to bring that column to great height. Now, there are exceptions. There's a couple of places where we see plumes out in the midwater, but on Earth, nothing penetrates up near the surface. This is a big question for looking at the plumes coming out of the South Pole of Enceladus and potential plumes on Europa as to what they indicate about what's happening on the bottom of the ocean. depending on interpretations of the nature of those ocean world oceans, they may be well mixed, they may be stratified, we don't know. But our calculations indicate buoyancy fluxes even lower than what you'd get from a high temperature. And it's because it's just, we're looking at fluids that are 10, 20, 40, 100 degrees warmer than the bottom, not 350 or 400. So I think that was part of the reason we're kind of curious about bubbles. Because it seems like in the Sue paper that interpreted the silicate nanoparticles to indicate active hydrothermal activity in the range of 90 to 140 degrees. The implication is that those particles were carried up through the water column, through the ice, and ejected into space and somehow survived. But they're quite small, and it's hard to know how you would do that, right? So our models don't speak directly to this question. I think it's a really important question because what it speaks to is how to interpret those observations in terms of not just what's happening on average in the entire ocean, but what might be happening on the seafloor. And I don't know that there's a mechanism that can carry tiny particles up through an ocean world ocean, through the ice and out into space in weeks or years. Right? And if you're going to mix the entire ocean, it seems like they would have ample time to dissolve, for example, before that would happen. So I think this is a really important question. And like I said, our models don't really address it. They just, what they essentially provide for the physical oceanographers is a lower boundary condition that they could apply to their simulations to see what kind of consequence circulation would occur.
The question, but first I have to make sure I understand the system. So I'm imagining that just like when you boil hot, you have heat at the bottom, you want to have the are still overturned. It's a lot easier to overturn water than it is rock. It's easier to overturn it if it's high permeability. So you have high enough permeability with water, and you're just making it conduct itself. And that's how I should be thinking about the system.
Well, I mean, these aren't really cells as much as they are, you know, this is just a cartoon, but it's the part of it that's the siphon. There's going to be a few streamlines that go all the way through. There'll be a few others that kind of corkscrew and they pop out. And most of them are just going to be bouncing around all over, not forming big stable cells, but
from an energetic
yes, from an energetic perspective. That's right. Yep.
Getting the least resistance.
Yep.
To go through. And so then you showed the lower gravity and you have like a bigger dipole pattern, which is consistent. You have a larger scale height with lower gravity, it's a bigger scale.
No, because we kept the geometry the same. So the dipole pretty much looks the same. It just slows down.
But I thought you said it was wider.
Well, what we got was the area right near the recharge side. It didn't start convecting locally right away. That didn't happen until the water got farther away from the recharge in those. So here I can pull that plot up again. The geometry is identical because.
But your gravity is lower, so your vertical scale height has to be
so the difference here is with a pot of water on the stove, there's no such thing as permeability. Ultimately, this system, the geometry is determined a priori by what we put into the model. How thick the permeable zone is and how far apart the two outcrops are. So there's almost no effect of gravity on the shape of convection I mean, it's subtle. You can see these cells are closer together, the upflow, downflow. Here, they're a bit farther apart. So those cells are a little bit wider, but that's still small scale.
Okay, so then maybe I'll just ask my question then, which is, do you expect, the scale that you get to actually be the same when you change your gravity? Or do you expect that the path of least resistance will actually set a different?
Yeah, okay, so maybe your question is more like this. Let me try, because I think that's a really good question. It's more like this. If you model this system where you let the convection go down all the way to the middle and form whatever shape it wants, and you change gravity.
Then you're gonna make your outcroppings at different places, and potentially do you expect them to have different typical size scales in those different systems?
I mean, the way we approach it is we don't let the outcropping occur where the fluid flows. It's the opposite. The way we model it is we predetermine the geology, and then we look at the consequent fluid flow. So
do they have a typical size scale, or do they have all different size scales?
I mean,
Like,
yeah,
like a full,
yeah,
equally likely to be any size scale.
So the seamounts follow a power law distribution. And that's where that estimate comes from. They can only see the big ones and they project down to the lower sizes and then estimate what the population is. And as far as spacing, again, we have no idea because most of the seafloor is not well enough mapped to see them on Earth. And so all I'll say is, I remember, the earliest seafloor hydrothermal circulation models were run in the late 70s and early 80s when we had no permeability data, and they all had giant circles that went into the mantle. And folks said, well, they form big circles, and therefore, if we look at the wavelength of heat flux, we can tell how deep the circulation is. Not so much. It's really determined by the layering and the properties of the medium. Is the problem. It's something that's a consequence of those pre-existing conditions. Now, obviously, there is a feedback because of reactions, right? If you have water-rock interaction and that serpentinite, you start with a chondritic material, you have which is essentially like peridotite in terms of being ultramafic. You have water-rock reactions, you create serpentinite, and that creates a combination of cracking at the margins and expansion internally. You're going to now create a heterogeneous network. I would guess that that's going to determine your flow pattern, not a characteristic shape, but the actual variability that is imposed on the medium. I don't know. I mean, I'm really off the reservation here in terms of like any knowledge about what those materials are. Yeah, Francis.
For what it's worth, IO is one place where we do know spacing of volcanoes.
Ah.
They look pretty evenly separated.
Okay.
They sort of avoid each other. So I have to guess that's what I would use.
Okay. Yeah, and for the big ones, we do have maps. And I've not looked at that. I suspect Paul Wessel and others have done that for Earth, but I don't know. I'd have to look at one of the census papers to see. But it's the case also that in much of the older seafloor. So the question came up earlier about steady state. We've had in the past, we've had different rates of seafloor production, different rates of volcanism, different rates of off-axis volcanism creating seamounts. And then much of that is buried now by thick sediments. It's a kind of a conundrum, is to really understand we can see what the distribution is right now, but that's going to be biased towards the most recent, probably the last 20 million years, just because those are the ones that are exposed. And as you get out to 30, 40, 50, 80 million years, you start to bury most of the features. And they won't even show up in the satellite maps, even if they're big, because there's not enough of a contrast in density between the rubbly piles and the consolidated sediment next to them. Like there's a signal there, but probably not enough to really make out. So I think it's a great question, and we just don't know. The other thing we don't know is why some of these are hydrologically active and others aren't. We've surveyed a couple dozen, and they're not all pumping water. Some are, some aren't. We have no idea. So even though you map out the features, they're not all active. So far, it's a really small sample. I'd say 10 to 20% from what we've seen. But again, it's a non-statistical sample. They're just places we happen to have.
May I suggest that we take one more question from the room and then we slowly transition to the social part where we can actually grab more food and
Sure, yeah,
discuss more.
I'll hang out. Yeah.
How should we think about sediments and ocean that doesn't have an atmosphere?
No, great question. So I had a section on it and I took it out because it was too long. Let me just say real quick. Another ocean world researcher, Noah Randolph Flagg, has a paper now in review, and it's based on a calculation of meteoritic deposition on bodies like range of ocean worlds, right? Based on calculations where they are within the solar system and so forth. And if material hits that icy shell, and if the shell is being cycled, right, then you can expect over the long period a rain of material through those oceans that's commensurate with the rain of material onto the ice, right? If the ice is mixing on a short enough time scale. To put this in perspective on Earth, the average sedimentation rate in the deep ocean far from continents is about 5 millimeters per 1,000 years, and a measurable fraction of that is meteorites, right? A lot of it's windblown dust from continental areas, but there's a measurable amount of meteoritic material. So one idea is you could simply have a thin veneer at the bottom. There are hypotheses that on Europa, there could be a gypsum layer that's precipitated from the water column. I know I've asked Francis about it. He's somewhat skeptical, and I need to read more about that possibility. But another way to think about it is that if you have a rind of altered material at the outer part of that core, that can function like a conductive boundary layer. It need not be sediment that's detritively deposited. It could simply be a contrast in properties. And in the case of Enceladus, which might be granular in nature, there's a vast literature on the breakdown of granular particles as they mix. It's often used in machine work. Parts get machined and they get thrown into a bucket of particles that are stirred and they knock out all the sharp edges. They consume themselves as well. So imagine a convecting granular core. I would suspect that those particles would grind against each other and potentially produce sediment, which would then segregate based on density. But again, who knows? I mean, there's a lot of options. So we're agnostic as to whether there is sediment on the bottom of any of these bodies, but I think there could be. And so it's worth exploring if there were, that layer basically serves two purposes. It's a lower conductivity material, and it's a material with lower permeability that can then be penetrated by cracks or faults or volcanic outcrops from an earlier period of volcanism or something. So yeah, that's a good question. And again, we're not going to know from Clipper.
That one,
Yeah, so I mean, I'd love to know.
we need the lander.
We need a lander, absolutely. And I don't mind which world they go to. Any of that would be great.
So I'm curious, and this is all beyond, but I'm curious, obviously with a body like Europa or Enceladus, there's quite a different gravity than Earth, and then there's the permeability, which is unknown. But there's also the fact that these are moons, that they're acted on by the much larger gravity of another body.
Oh,
And at least in the case of Europa, to my understanding, there's a gravitational interaction with other moons, isn't there? So I'm curious, that obviously produces tidal forces that are pretty different from what we see on Earth. I'm curious, would that in any way affect geothermal flow, and is there any way to model the effect it might have?
yes and yes. That's a great, yeah, again, we started simple, but you're absolutely right. These simulations do not include tidal pumping. They do not include tidally induced circulation. And you can imagine a system where you're generating heat either internally or at the base, and now you tidally force flows. Absolutely. And that could essentially dominate and knock down our flow patterns, right? If there's enough tidally induced circulation. So game on. I mean, all of these things should be simulated. Absolutely. Yeah, that's a great question. Yeah. Yeah. No, I think you're absolutely right.
Noémie, did you say there was a question on Zoom?
No question.
Okay. Well, thank you for sticking around on a Friday, and I really enjoyed this, so I appreciate your being here.